right, let's continue with the curl geodesics. We have discussed a little bit the light-like geodesics, only very few aspects. And today I want to talk about the time-like geodesics again. This will be, just concentrating on a few aspects. As I said already, the geodesics in curl spacetime are very rich, very they have many features, and one could easily talk a whole term about geodesics in the curl spacetime. I don't want to do this. Just highlighting a few aspects. What you will need for this, for the discussion today, is the theta and the r component of the geodesic equation, and now for time-like curves. So we had this expression, rho to the 4 theta squared. Then the same term which we had for the light-like geodesics, minus, A over C sine theta E. So that was it for the light-like geodesics. And now we have the term with the epsilon, which for time-like curves is C squared minus C squared A squared cosine squared theta. And the equation for r dot squared, this was minus delta k plus r squared plus a squared e over c minus al squared. This is also squared here, I forgot a square. Minus c squared r squared delta. Well, I hope everybody remembers what rho and delta was. Just to remind you, rho was this. That's a quantity which becomes 0 at the ring singularity. And delta was this here, which becomes 0 on the horizons. And we will assume, as we did last time, that we have a black hole spacetime. This means a spacetime where the a square is smaller than m squared, so that we indeed do have 2 horizons. Okay, and the first aspect of the time-like geodesics I want to discuss a little bit is the question of circular geodesics in the equatorial plane. So I say already in advance that I will not present the full calculations, because it will would take a lot of time and would be it's a rather awkward expressions. Maybe I type out a little bit more in the lecture notes than I do on the board, but on the board I will just sketch the general idea how to get the relevant equations. So if we are in the equatorial plane, so what I want to discuss is circular time-like geodesics in the equatorial plane. That's the first issue. Hope everybody remembers how the situation was for the Schwarzschild case. The Schwarzschild case, we had circular geodesics in the equatorial plane, where every plane through the origin was an equatorial plane in the Schwarzschild case. And we did have time-like circular orbits. Do you remember up to which radius in the Schwarzschild case? Yes, 3 rs half. This is in these natural units 3 times m, the little m, which is g times capital M over c squared. So this was, and why? Why did it stop at r equals 3m? It stopped there because at this value, a geodesic would have to move at the speed of light in order to stay at this radius. So that's a limiting case which can be approached arbitrarily closely, but it cannot be exceeded. And beyond this, on the other side, this is still outside of the horizon, right? The horizon was at 2m. Between 2m and 3m, there are no circular time-like geodesics in the Schwarzschild case. And we will discuss how this situation changes for a spinning black hole. And then for the Schwarzschild case, we also discussed the question of whether these circular geodesics are stable. Do you remember up to which radius they actually were stable? No. These are the ones which, from which if you perturb them, they can escape to infinity. Yeah, they are sometimes called marginally bound. This was 4m. No, the innermost stable circular orbit, the so-called ISCO, was at a different radius. This was at 6m. 6m, yeah. So 3 RS. Yeah. So this is quite important if you discuss the question of how close to a black hole you can orbit. In the case of the Schwarzschild spacetime, you can orbit in free fall, in free motion, without a propulsion, on a stable orbit, only up to 6m. And we have calculated in one of the worksheets what gravitational time dilation you can get out of this effect. Yeah? If you move towards a black hole up to this orbit and then spend some time in this orbit and then move out again, what is the time dilation in comparison to an observer who had stayed outside? And the effect was not very strong, actually. You could get something in the order of a factor of 2 or 3 or something like that, not more than that. So you cannot have strong time dilation effect just by spending a certain time orbiting a Schwarzschild black hole. You will see that it's completely different for a Kerr black hole. Actually, the time dilation factor can be arbitrarily big. That's what we will discuss today. Okay, so which equations do we need? These two equations, of course. I should mention that I already mentioned this, but let me repeat it, that you can completely decouple the equation by introducing a new parameter. This was our affine parameter. Now, as we are discussing time-like geodesics, the parameter is proper time. Yeah? So the dot means derivative with respect to proper time. You see, this expression depends only on theta, this only on r, but on the left-hand side you have the rho which depends on both. And you can get rid of this coupling by introducing the so-called Mino parameter. I denoted the derivative with respect to the Mino parameter by a prime, and then the equations look like that. So the prime is just defined by the property that it is a dot multiplied with rho squared. Yeah? D by d tau, that's a dot, times rho squared is d by d lambda. Lambda is a Mino time. So then we have the equations completely decoupled. And in this first step I want to discuss geodesics in the equatorial plane. So we have theta equal pi half, and then we could see what comes out of the first equation. On the left-hand side we have a 0, because if theta is a constant, then c dot or c prime is 0. And on the right-hand side we have k minus L, sine theta is 1, if I'm in the equatorial plane, minus A over c, and that's it, because the cosine is 0. So this gives us a k. Yeah? So we can, from this equation, we can express k in terms of L and E. And the second equation then gives us r prime squared is minus delta k plus r squared plus a squared ec minus al squared minus c squared r squared delta. And here I can insert this expression for k. So k is plus this bracket, L minus a over c e squared. So this is r prime squared. Let me write it again. Plus r squared plus a squared e over c minus al minus c squared r squared delta. Okay. And now I want to have circular geodesics. And this means that I have r prime equals 0 and r double prime equals 0. Or maybe I could calculate r double prime first, maybe that's better. So I differentiate this with respect to the parameter lambda, and I get 2r prime r double prime. And now I differentiate this whole expression with respect to r. So delta is here written on the board. If I take the derivative, I get minus 2r minus 2m. This is a constant, so it's unchanged. And if I differentiate this, I get 2 times the bracket. A squared e over c minus al. And then the inner derivative 2r e over c. And then the last term is minus c squared 2r delta minus c squared r squared, and the delta differentiated 2r minus 2m. Bracket close. I have differentiated with respect to r. On the left-hand side, I differentiated with respect to the curve parameter. So I have to differentiate r with respect to the curve parameter, which is a amino parameter in this case, and then I get this. And I think 2r prime drops out. 2, 2, 2, 2, and the r prime is gone. So this gives me r double prime. And now I do what I've already anticipated. I consider circular time-like geodesics. So I have the equations r prime equals 0 and r double prime equals 0. Okay? And now you see what we get. I think I write this on another board. So I have 0 is r prime equals 0 minus delta r squared plus a squared e over c minus al squared. It's nonsense. Minus delta k. Oops. Minus delta k. And k I've already calculated. Okay, let me begin with this term. And then minus delta k. And k was L minus A over C E squared. And the last term is minus C squared R squared delta. And then I have the second equation. This is r double prime equals 0 is minus r minus m. R minus m. Then comes the k. This is L minus AC E squared plus this bracket here. E over C minus AL times 2R E over C minus C squared R delta minus C squared R squared R minus M. Okay, so what do these two equations tell us? Well, let's recall how it was in the Schwarzschild case. In the Schwarzschild case, A equals 0, you see that in the bracket we have only one term. Yeah? If A is 0, we have only one term in the brackets. This means there are no mixed terms, E times L. Yeah, in the Schwarzschild case. In the Schwarzschild case, there are no terms E times L. There are only terms with E squared and terms with L squared. And we could solve these two equations for E squared and L squared. So in the Schwarzschild case, we got equations of the form, and actually we calculated them. E squared is f1 of r, and L squared is f2 of r. And the condition for circular geodesics was then that these two terms must be bigger than 0. Actually, this gave only one condition, and it gave the condition that R must be 3m, or as we wrote, 3rs half. So that was his calculation in the Schwarzschild case. Now you see in the Kerr case it's considerably more complicated because we have mixed terms, terms E times L. So we cannot just solve the equations for E squared and L squared, but we can solve them for E and L, but they become quadratic equations. And if you have a quadratic equation in a non-trivial way, so that it's not just of the form L squared is something, it's really a non-trivial quadratic equation, then you have plus minus a certain square root. And the thing under the square root must be non-zero. And because you have two signs, plus and minus, you get two different conditions. Is this physically understandable? Why do we get, here we get only one condition. Here we get, sorry, what did I write here? This is bigger, this was correct, but this here was of course bigger. Yeah, this was a condition. This must be bigger. The expression r minus 3m was in the denominator of these expressions. Yeah? So it cannot be 0. It must be strictly bigger than 0. So these expressions were something like a positive quantity divided by r minus 3m, and the whole thing must be bigger or equal than 0. So r must be bigger than 3m. So in this case, we got one condition, which meant that there's one radius value which gives a limit for the circular light-like geodesics. Now with a different from 0, we have to solve quadratic equations. We had two solutions, plus minus solutions. And is this physically understandable? Yes, I think it is. Because now we have to distinguish between the co-rotating circular geodesics and the counter-rotating. Yeah, our black hole is rotating. So if we have A positive, then with our choice of the coordinates, it rotates in the positive phi direction. Yeah? So you can easily imagine, just intuitively, that a particle orbiting in a circle in the equatorial plane will be influenced by the gravitational field in a different way. If it co-rotates, as it also moves in the positive phi direction, or if it counter-rotates, because of the dragging by the black hole. So that's the reason why we get two solutions. Yeah, so in the Kerr case, we actually get two solutions. And I will not work this out. Maybe I type it out. I have to see. But the equations become really ugly. Yeah, you have to solve. If you multiply this out, you get an equation of the form something times E squared plus something times L squared plus something times E times L plus a rest. And it's an equation of the same form from the second equation. So you solve one of them. Well, you can add them together in a way that the mixed term drops out. So you can relate L squared to E squared. But then you have to solve a quadratic equation. You can solve it either for L or for E, and to get this plus minus sign into the game. And that's the reason why you get two solutions. So in the Kerr case, we have quadratic equation for E and L. And therefore, we have different conditions for co-rotating case and counter-rotating. Time-like geodesics. Okay, if you work this out, so you solve for E and for L, you have on the right-hand side two expressions with a plus minus. And this gives you conditions on R. Yeah? So you have the condition that what you have under the square root must be positive. This gives you a condition on R, and I just plot the result. So I do not work out the details here. Actually, the expression becomes surprisingly complicated. In this form, it doesn't look so bad. But if you start writing it out, it becomes really, really ugly. So I decided not to do this on the board. So what you get is, the usual way of plotting this is that you plot here your spin parameter, and you want to have a black hole, so we consider it only up to m. Without loss of generality, let's assume A is positive. Yeah, so the black hole rotates in the positive phi direction. And here I want to write where the time-like orbits are, where the last time-like orbit is. We have already discussed that for the Schwarzschild case, it is by 3m, at 3m. Yeah, A equals 0 is Schwarzschild, so it must start here. And then you have two solutions, and what you get is the following. One branch goes to m, it goes like that, and the other branch goes to 4m. Oops. So it does something like that. Yeah? So this is, wait a minute, the smaller one is co-rotating. Co-rotating. And this is a counter-rotating. So the allowed values for the co-rotating, the allowed radius values for the co-rotating circular geodesics are the values above this line, and for the counter-rotating ones above this line. So in the extreme case, A equal m, I am at m. But this is also the horizon, right? Remember, this is also the horizon. If the horizon starts at 2m and also goes to m. Yeah? The dashed line is the horizon. Let me remind you where the horizon was, just in case you forgot it. So the horizons were at delta equals 0, which is r squared plus a squared minus 2mr. And if I solve this quadratic equation, I get r plus minus is m plus minus root m squared minus a squared. And you see, if you have m equal a, then the two horizons coincide. That's the so-called extreme case, and the degenerate horizon is at r plus minus equal m. And the co-rotating circular time-like geodesics, they arrive at exactly this value. So this means in the extreme case, you can move on a time-like, in free fall on a time-like circle at radius values arbitrarily close to the horizon. So you don't have this gap which you have in the Schwarzschild case. There's this gap between 2m and 3m. Okay, this is for just for time-like geodesics. It's not just for stable ones. What do we have in order to discuss stability?
The second derivative.
Second derivative, yeah. We have r prime, we have r double prime, we have to calculate the third derivative. And the third derivative is, when the third derivative is negative, then we have stable orbits, and if it is positive, we have unstable orbits. And the borderline case is the one where the third derivative is 0. That's the innermost stable circular orbit. Actually, the word is bad. It is misleading because the orbit is not stable. Yeah, if you say innermost stable circular orbit, this suggests that the orbit is stable, but it is not stable. It is stable only with respect to perturbation in one direction. Yeah, it's a saddle. So it's stable in one direction and unstable in the other one. So it's actually it's the first orbit which is not stable. Yeah, one should say the first unstable orbit. This would be a better name, but it's common to call it the innermost stable circular orbit. So again, I won't do the calculation. So we would have to calculate the third derivative. So should I write this here? The third derivative is, there's a minus sign, and this gives a 1, so I have minus L minus A over C A squared. Then let's begin with this differentiation. Then I have 2 E over C R squared plus A squared E over C minus AL. Then I have to differentiate this here. Plus 2R E over C, and the same thing again. So everything squared. And here I get minus C squared delta minus C squared R to R minus 2M. This I get, this comes again, right? Or let me write it in this place. This is R cubed, so this gives minus 3C squared R squared, and plus C squared 2 times R. That's it. So now we have 3 equations. We have 3 equations. R prime equals 0 if we want to find the ISCO. Yeah, the one where this is where we have a saddle. So the side derivative is also 0. So this must be 0, this must be 0, and this must be 0. Now we can solve for E, L, and R. Yeah? And the expression for R, this gives us the ISCO. So if all 3 are 0, gives the ISCO. And again, we can plot this. So I don't do the calculation for this on the board. I just plot. So here I have the time-like orbits, time-like circular orbits. And here I want to discuss time-like circular stable orbits. So, oops, yes, no, not MA. We go up to the extreme case. Here's the R coordinate. So in the Schwarzschild case, we began at 6m, right? There was the ISCO at 6m. And again, if you do the calculation, this goes down to m. And this is for the co-rotating case. And the other one, this goes out to 9m. So the counter-rotating ISCO is at 9m for the extreme case. So if you have an extreme Kerr black hole, you can move in the co-rotating way very close to the thing, but in the counter-rotating direction, if you want to be on a stable orbit, you have to be comparatively far away. Did I make a mistake again?
Well, I can't understand what's written there in the lower. Is it plus but before 2R E over C a little bit lower?
Oops.
The next to last
Yeah.
string.
I forgot an M, right?
No, I meant not that. I meant it's, there's a term 2R E over C squared in this line.
2R over C. Here?
Yeah.
This term comes.
In brackets, I think. Yeah, in brackets.
This one.
Yeah. So.
Yes, 2R E over C times 2R E over C gives this.
Does it have plus before it? Yeah.
It has a plus, yes.
Okay.
I think that's correct.
Yeah.
Okay, so this is the result, what you will find if you do the calculation. And this means that actually if you have an extreme black hole, that then you can be in a stable orbit arbitrarily close to the horizon. Actually, there's a caveat. When I say arbitrarily close, I mean in terms of the Boyer-Lindquist coordinate. Yeah, the Boyer-Lindquist coordinate for the horizon, let me plot again the horizon here. The horizon goes from 2m to m. And that's a r plus. I should write horizon at r plus. There's another one which comes out of 0 and goes to m. Yeah, this is a horizon r plus. So actually, the Boyer-Lindquist coordinates become they are irregular. They are not well defined at the horizon, right? At delta equals 0, I have the delta is in the denominator of the metric. Yeah. So at delta equals 0, the metric has a coordinate singularity, and this means that the distances in terms of the r coordinate, they cannot be associated immediately with physical distances. And actually, this becomes particularly bad in the extreme case. If you are at the extreme case, actually, you will find that the horizon is, if you calculate proper lengths, not the r coordinate, but really proper lengths. Yeah, you integrate the length element measured with the metric, that this actually becomes infinite. The horizon is infinitely far away from anybody who is outside of the horizon. So the fact that this approaches the same coordinate doesn't necessarily mean that actually the distance becomes 0. Actually, the distance stays finite. Yeah, if you calculate the proper distance, you will see that it stays finite. Although in the coordinates, both things approach the same value m. Yeah, because the coordinates are pathological, they are not well defined at the horizon. This is no contradiction. And I think we will make a little exercise about this. We will check that actually the distance is finite between this innermost stable circular orbit and the horizon, and also between the innermost time-like orbit. Actually, the limit orbit is then light-like, of course. Yeah. No, I should point to this curve. Yeah, this curve. The limit curve is a light-like curve. Yeah, the time-like ones are above the line, and the limit curve is a light-like geodesic. So we will do a little exercise verifying that actually the distance in terms of proper length stays finite, and we will calculate the time dilation effect for an observer, and this actually will go to infinity. So actually you can have arbitrarily strong time dilation effects if you orbit a Kerr black hole in the proper sense. If you do it in the counter-rotating sense, then the effect is weaker than it is for Schwarzschild. But if you do it in the co-rotating sense, then it can be arbitrarily large. Another question or comment?
Is it really so that we cannot achieve the horizon? Because I thought that it is so only when the black hole is not extreme. That is to say, it has some delta, some distance from A equal to M. It's not exactly A.
Yeah.
But in the case when we have a really extreme Kerr black hole, does it also mean that we cannot move on the horizon, the distance?
Well, you can never move on the horizon.
Yeah,
the horizon is light-like.
Yeah.
You can cross it in one direction, but you cannot stay on the horizon unless you are a photon. Photons can do this, but we cannot do this. So you cannot be exactly at the horizon. But as an object that moves at subluminal speed, you can for the extreme case, and only for the extreme case, you can orbit on a circle in free fall arbitrarily close to the horizon. In any other case, if the A is smaller than the M, in any other case, if A is smaller than M, you have a gap between the horizon and the innermost time-like orbit, stable or unstable. Yeah? As it is in the Schwarzschild case. In the Schwarzschild case, you also have this gap between 2M and 3M, between the horizon and the time-like circular orbits. And when I said in the extreme case you can come arbitrarily close to the horizon, then I meant arbitrarily close in terms of the r coordinate. Yeah? I did not mean arbitrarily close in terms of proper length. We will discuss this difference in the worksheet. I think in last week we have we have done some rather insightful calculations which demonstrate that coordinate pictures, as a geometry as it looks in the coordinate system, can be quite different from the intrinsic geometry. Yeah, we have calculated the sphere or the hemispheres at r equals 0. In the coordinate pictures, these are really hemispheres, but by its intrinsic geometry, these are flat disks, as we have calculated in the worksheet. So you always have to be careful when you interpret coordinate pictures, you have to be careful that you do not misinterpret it as the intrinsic geometry. Yeah. The intrinsic geometry might be something quite different. In the Schwarzschild case, it is the same. Yeah? In the Schwarzschild case, the sphere really is a sphere with its intrinsic metric. Yeah? It is what geometers call a round sphere. But in the Kerr case, it is not so. And similarly, proper lengths are not immediately related to the r coordinate. That's the same thing in the Schwarzschild case. In the Schwarzschild case, the r coordinate has a meaning that the circumference of a circle in the equatorial plane at radius coordinate r is 2 pi r. Yeah, so it's a circle. The circumference is directly measured by the r coordinate. But if you go along a radial line, the measured distance, measured with a metric, is different from delta r. Yeah? So r is not a distance from anything. Yeah? It's a measure for the circumference of circles or for the area of spheres. Okay, so much very briefly without doing much detailed calculations on the circular time-like geodesics in the equatorial plane. So the relevant equations are on the board. So I think everybody should be able now to do the calculations by him or herself. But I warn you, it will take some time. Okay. Of course, it's discussed in many books. So Chandrasekhar, for instance, discusses the time-like geodesics in great detail. Or O'Neill discusses them in great detail. So if you want to see all the details, then you can look into one of the books. So this was the first thing I wanted to do, talking about circular time-like geodesics in the equatorial plane. And then I wanted to make a few remarks about the general features of the theta motion. Yeah? So we have orbits in the equatorial plane, but we have, of course, also orbits off the equatorial plane, and they are quite different from what we are used to from Schwarzschild. In the Schwarzschild case, every orbit is in a plane. It's in some equatorial plane, some plane which goes through the origin. If you choose a coordinate system such that this is not the equatorial plane but some other plane, but then it's still a plane. So what does the theta coordinate do? The theta coordinate oscillates between a maximum and a minimum. So it goes through the equator, minimum value, equator, maximum value, equator, minimum value, and so on. And you will see that in the Kerr spacetime, quite different theta motions are possible. There are motions where the orbits never cross the equatorial plane. So they stay either in the northern hemisphere or in the southern hemisphere. That's impossible in the Schwarzschild case. But in the Kerr spacetime it's possible. So let's discuss some general features of the theta motion. Oops. Where's the board here? So the theta motion of time-like geodesics. So now we will work with this equation here. Let me write it again, and then I will rewrite the right-hand side in a certain way, which will be more convenient for us. So this was k minus L over sine theta minus A over C. Sine theta E squared minus C squared A squared cosine squared theta. And well, now we have sine theta terms and cosine theta terms, which is a little bit inconvenient. Let me express everything in terms of cosine. So I pull 1 as a factor in the denominator out of the bracket. then I have a sine theta squared here. So and inside the bracket I have L minus AC E sine squared theta, which can be easily expressed in terms of cosine. And I will do this in a minute. That's the c, speed of light. So if I multiply this bracket out, I get k minus 1 sine squared theta, L squared minus 2L AE over C sine squared theta plus A squared E squared C squared. Wait a minute. Yes, it's in front of the bracket, then it's correct. Oops. So you see a few terms drop out. So this is L over sine squared theta. I leave a gap here. Then I have plus 2L AE over C. The two sine theta terms cancel. And I have minus A squared E squared C squared sine squared theta. Okay. So I wanted to express everything in terms of cosine. So let me write here cosine squared theta plus sine squared theta. That's a 1, of course, yeah? So I didn't change anything. But now I can collect terms with the cosine squared. And for this I can write 1 minus cosine squared theta. So let me collect all terms which have no theta dependence. It is this here, minus L, wasn't it L squared? L squared was L squared, right? Yes. So I have minus L squared, that's this here. This has no theta. This with the 1 has no theta. And now the cosine squared terms. So I have minus L squared over sine squared theta. Minus gives plus A squared E squared over C squared minus C squared. Okay. And this is again a square, right? This is anything wrong?
I maybe forgot an A squared from the in the last term, C squared, A squared.
Yes, thank you. There's an A squared missing. Where was it? Here, right? Okay, that's it. And this is a square here. These three terms give a square. So we have, theta prime squared is k minus L minus AE over C squared. You see, if I multiply this square out, I get minus L squared plus 2L AE over C minus A squared, E squared, C squared. And the rest is what it is. Cosine squared theta. Yeah, if I want to express everything in terms of cosine, I could write it in this way. Plus A squared E squared divided by C squared minus A squared C squared. Okay. And here we have a combination of our Carter constant with the other two constants of motion, which very, very often occurs when one is doing calculation with geodesics in the Kerr space-time, and it's common to abbreviate this by Q. And well, we are working with the constants of motion epsilon, L, E, and K. But you can equally well work with the constant of motion epsilon, E, L, and Q. They contain exactly the same information, and many people do this. And if they do this, then they also call this Q, the Carter constant. Yeah, so the name Carter constant is used for K and also for Q. So you have to be careful if you read a paper or if you read in a book about the Kerr metric, when they speak about the Carter constant, what do they mean? Do they mean the K or do they mean the Q? Actually, the K is, excuse me, the K is maybe a little bit more easier accessible for interpretation, because in the Schwarzschild case it becomes just the square of the angular momentum. Yeah, the vector L squared. This is a K. This has no obvious, well, in the Schwarzschild case, you see what it is. A is 0. Then you have K minus L squared. L is the Z component of the angular momentum. So the Q in the Schwarzschild case is the component of the angular momentum perpendicular to the Z direction. Yeah? It's the Z and the X and the Y component added up and squared. So, well, it also has an interpretation in the Schwarzschild case. Anyway, so you see that, the sign of the whole thing, the right-hand side must be positive, right? Because this is a square. The right-hand side must be positive, otherwise the expression cannot hold. So you see, this is strongly influenced by the Q, and we can actually now discuss the three cases: Q bigger than 0, Q equal to 0, and Q smaller than 0, and to see what kind of restrictions on the theta motions these geodesics have. So that's the usual way in which you classify the time-like geodesics, and also the light-like geodesics, by the way, in the Kerr space-time with respect to the theta motion. Here you distinguish the case Q bigger than 0, Q equal to 0, and Q smaller than 0. So let's begin with Q bigger than 0. Or maybe I should, as a preparation for the discussion, I should write this maybe in a slightly different way. You see, the right-hand side depends only on cosine squared of theta. So one could view this as a kind of effective potential in terms of the variable cosine squared of theta. So for this reason, it would be convenient to have on the left-hand side not the derivative of theta, but the derivative of cosine squared of theta. Yeah, so let me substitute this. Let me write u is the cosine square of theta. And then I have u prime. What is this? This is 2 times cosine theta, and if I differentiate the cosine, I get the minus sine theta, theta prime. And if I insert this, then my equation becomes what? So I have u prime squared is 4 cosine squared theta sine squared theta, theta prime squared. And theta prime squared I have just calculated here. So this gives 4 cosine is u, sine squared is 1 minus u, is that true? Let me see if this, it is 2, it is 2. I have the thing in the denominator, I forgot this. So then I have the theta prime squared. I just introduce this, q plus cosine squared is u, and then another bracket minus L squared, this is 1 minus u, plus a squared, e squared, c squared, minus a squared, c squared. Okay, and you see this is, well, I leave 1 u, or 4 times u in front of everything. And then I have a quadratic function, right? I have 1 minus u times q minus, this cancels, minus ul squared, and then plus u times 1 minus u a squared, e squared, c squared, minus a squared, c squared. So you see this is just a quadratic function, right? Linear, linear, here quadratic. So if I call this, if I call this, say, t of u, then t is a quadratic function. And we have to discuss this. U is positive. Yeah, u is cosine squared of theta. So we have to discuss the sine of t of u. And we observe that t of 0, what is that? Cosine theta equals 0, that's the equatorial plane, right? So this corresponds to theta equal pi half. T of 0, what is this? This is q. This is gone, that's it. It's q. So q, the sign of q decides where the function t starts. T is defined on the interval 0 to 1, right? The argument is the u is cosine squared of theta. This can take values between 0 and 1. So it begins with the value of q, and it ends at t of 1. What is this? This is 0, minus L squared, and this is 0. So it ends at minus L squared. And yeah, we can discuss the possibilities now, which give us the three types of orbits I want to discuss. Let me see, maybe I leave the equation. Yeah, I think I can erase this. Oops. So we will now discuss the three cases. Q bigger than 0, equal to 0, or smaller than 0. Okay. So let's assume Q is bigger than 0. So what's the possibilities for the function t? So the function t is defined on the interval between 0 and 1. And it is a second order function. Yeah? It's a function of second order. And it determines the sign of u prime squared, because u is positive. U is cosine squared theta. So we have to see if it starts at a positive value. It starts here at q. And it's a parabola, right? A quadratic function is a parabola. Where can it be positive? So there are the following possibilities. And at 1 it takes a value minus L squared. Yeah? Okay, so actually there are two cases. L could be 0. L could be 0. Then it would go through this point. You would see then it could stay behind the, it could stay above the 0 line everywhere. This would be an orbit. So, okay, let me begin with this case. So if L is equal to 0, then I could have something like that. Yeah, that's a parabola. So the curve would be everywhere above the 0 line. This would mean the whole region would be allowed for our curve. This would be an orbit which goes through the axis. Yeah, here's the equator, here's the axis. Yeah, cosine theta equals 0 means equator, cosine 0 equal 1 means axis. So it goes through the axis. So this is an orbit which where the theta coordinate ranges over all possible values, and it goes through the axis. So it could be a motion of this kind, for instance. So that's possible. If L is different from 0, then it must be something like that. And it begins at a positive value, so it has to end here. And now you see, if you have the parabola opened in this way or opened in this way, in any case, you get one intersection with a 0 line. Yeah, so in the first case, this would be the allowed values, and in the second case, these would be the allowed values. In both cases, it would be an interval which extends to the equatorial plane. Yeah? And now look at the equation for, in the first line, it still is for theta prime squared. It involves only cosine squared theta. This means it is symmetric with respect to the equatorial plane. Yeah? Cosine squared theta is an expression which is symmetric with respect to the equatorial plane. So when it moves between from this value to the equatorial plane, then it has to move symmetrically in the other direction, also into the other hemisphere. So it would be an orbit which would oscillate about the equatorial plane, both for this case and for this case. Question?
Why is this second graph not possible for L equals 0?
I'm sorry?
There are two.
Yes, both are possible. Both are possible.
But why is the lower one not possible for L equals 0?
Oh, it is possible, but then it is. Oh, wait a minute. Oh, thank you. You're right. You're right. This is also possible. Yes. So this was only one possibility, that it extends to the equator. It's also possible that it does not extend to the equator. Actually, there are orbits of this kind. They are quite funny. They go through the axis, but they don't reach the equator. Yeah. So they oscillate between extremal values of theta, and they go through the axis. Yes, thank you. That's also possible. And so this means these are polar orbits. Yeah, orbits through the axis. That's what polar orbit means. Orbits through axis. And they have L equals 0. Yeah, L equals 0. There's this characteristic for orbits that may go through the axis. And these are orbits that oscillate around the equatorial plane. And that's it, what is possible for Q bigger than 0. Yeah? So these are orbits of the kind, well, with this exception, these are orbits which we also know from the Schwarzschild spacetime. Yeah? If you have a Schwarzschild orbit which is in a plane, which moves between a minimum value for theta and a maximum value for theta, it would be something like that here. Yeah, so this would be the extremal value for theta. Yeah, because of the symmetry, it must be the same value. The maximum and the minimum must be the same value. So these are quite ordinary orbits which we are used to. These are the ones with Q bigger than 0. Let's talk about Q equal to 0. Q equal to 0. Then we have, of course, the possibility that the orbits are equatorial. Look, if you look at the first line, if Q is equal to 0, then of course theta equal pi half is a solution. As in the left-hand side is 0, and the right-hand side is also 0 because the cosine is 0. Yeah? So one solution would be geodesics in the equatorial plane. So let me put it this way. This was here case A, this was case B, and here again we have an A, and then we have a B. Let me see. This is my function. So it has now to end either here or here. Okay, let me do again this case that L is 0. Then it has to end here and it starts here. There are, of course, orbits of this kind. So it ranges over the whole available interval and approaches the equatorial plane here at the left hand of the picture. And whereas the other one, that it is opened in this way, this of course gives no allowed orbits because then I have no positive values. And another possibility would be that I have L squared different from 0, and it must be here. And the only case in which we can realize this is this here. So then we would have only a certain theta coordinate available. So it has a certain maximum theta value and approaches the equatorial plane for this, here at this lower end. And actually, if you analyze this further, you see that there are two ways in which this can happen. Either here we approach the ring singularity, that's one possibility. And the other possibility is that we approach the equatorial plane asymptotically. Actually, we cannot, for instance, touch the equatorial plane. That's impossible. That it makes something like that. Yeah, that it has a minimum, touches the equatorial plane, and then goes up again. From this diagram, you cannot read this. But if you calculate the second derivative, if you calculate theta double prime from the first line, you see actually that at the equatorial plane, cosine theta equals 0. It's identically 0. Yeah? So it cannot be a minimum or a maximum in the sense that really the second derivative is different from 0. Yeah? And because the geodesic equation is a second order equation, it follows that if the second derivative is also 0, then it must be inside the plane. Yeah? So the case that it touches and peels off again is impossible. So these are the cases Q equals 0. So the most prominent elements in this family are the geodesics in the equatorial plane. So the circular orbits about which we have talked a few minutes ago, they are in this class. They have Q equals 0. And now comes the most interesting one. Now comes Q smaller than 0. And these are the geodesics which are called vortical. Maybe you have heard this name. And that's something which doesn't exist in the Schwarzschild spacetime. It's characteristic of Kerr and other rotating spacetimes. So what can we have if Q is smaller than 0? So if Q is smaller than 0, let's again do the case L equals 0 first. 1. So then it has to go through this point, but Q is now smaller than 0. So the only case would be something like that. And case B would be that T of U, that's U, would be that L is non-zero. So then we have the graph going through this point, and it begins at some negative value Q. And if it should take some positive values, if it is really an orbit where this equation is satisfied somewhere, where the right-hand side is positive somewhere, then it must have two intersections with a 0 line. So the allowed region would be this here. The allowed region would be this here. This here would be again a polar orbit. And this would be something really funny, right? So the orbit is confined to two cones, sorry, 2 cones. So the orbit, this is the allowed region. Yeah, so we have a theta 1 here and a theta 2 here, and this corresponds to these values. Yeah, u is a cosine squared of theta. So this is cosine squared of theta 1, cosine squared of theta 2. So this here is, oops, theta 1. And no, the bigger one is, wait a minute, the cosine, let me see. The cosine begins at 1, this is the equator. So here's the cosine is 0. So this is closer to the equator. Yeah, just the other way around, right? This is theta 2, this is theta 1. Yeah, here's the equator, here's the axis. So theta 1 is closer to the equator. And this is confined to this region between the two cones. It can touch the boundary. Yeah, at this point, theta prime must be 0, so there's a turning point, and then it may touch the other cone, so it can perform a motion of this kind. Yeah, between these two, and these are these famous vortical geodesics. So they could go through from big radius values to minus infinity. Yeah? Remember, when we draw pictures of the whole curve space-time, we have at the origin of our coordinate system r equal minus infinity. Yeah, r equals 0 is a sphere of finite radius. Here's the ring singularity. And here are these throats, r equals 0. And these geodesics, they could pass through the throats. There would be nothing particular at the throat. We have discussed this in the last worksheet. For a big black hole, for a supermassive black hole, this is perfectly harmless to pass through this area. The tidal forces are very mild there for a supermassive black hole. And then the geodesic could go out to minus infinity. So it could go all the way from plus infinity to minus infinity without ever touching the equatorial plane. In particular, without touching the ring singularity. And actually, you could move along such a geodesic. So if you drop from a big height into a black hole, if you don't have a particular tangential motion, if you really drop from rest in the coordinate system we are using here, tangential to a T-line, actually you will follow such a curve. You will pass the outer horizon, you will pass the inner horizon, you will pass the throat, and then you might go out to minus infinity. So these are, this is this class. There's also a special case where the two zeros coincide. Yeah? Then there's just one point which is allowed. So these were, let me write this. It's a special case of B, but it's so important that I consider it separately. It could be like that. Oops. That I have just one particular point which is allowed. One particular theta coordinate is allowed. This means the whole orbit is on a cone. Yeah? The whole orbit is contained in a cone. It's contained in a surface theta equal constant, but not theta equal pi half. That would be here. We know that this exists. Yeah? But in the curve space-time, it's also possible for theta values different from, and actually, that's a limiting case of this class of geodesics, which are between two cones. Yeah, the limiting case is that the two cones come together, and then the geodesic moves just on a cone. And again, this is something which is not possible in the Schwarzschild spacetime unless you are in radial motion. In radial motion, this is possible, yeah, but not with a phi motion. Okay, so this was a brief overview of the possible theta motions. So there are three classes. These are the orbits which oscillate around the equatorial plane. That's what we're used to from Schwarzschild. In particular, this is the case for bound orbits at big radii. Yeah? At big radii, the orbits are very similar to Schwarzschild, and at even bigger radii, even very similar to Newton, to the ordinary Kepler ellipses, yeah? The bound orbits. So they are, of course, of this class. Yeah? So the Kepler ellipses are as limiting or as approximative cases contained in this class. So they have Q bigger than 0. Then we have the geodesics in the equatorial plane with some special cases where the equatorial plane is approached asymptotically, or the ring singularity is approached. And then we have, as a completely new feature, these vertical time lag, and there are also time light-like vertical geodesics. So they are a new feature. Well, actually, we have discussed some light-like vertical geodesics, namely the principal null geodesics. The principal null geodesics, if they are not in the equatorial plane, the one in the equatorial plane hits the ring singularity, and then they crash, so to speak. But the other ones, they move in along a theta line. Yeah, they have theta equal constant. So they move in, and they move from plus infinity, r equal plus infinity, to r equal minus infinity. They go through, they cross the throat at r equals 0, and they go all the way from r equal plus infinity to r equal minus infinity. And there are also time-like geodesics of this kind. They are associated with a picture like that. Okay, so this was the second feature of time-like geodesics I wanted to briefly discuss. And then the third one is, this is about linking the Kerr geodesics to observations which we can already make at a time where we do not have observations close to a black hole available. We might ask ourselves, is the Kerr metric, can we use it also as a reasonable metric for rotating objects which are not black holes? And are there then interesting new qualitative features of the geodesic equation which can be tested with rotating objects? And actually this is true. We can use the Kerr metric at least as an approximation for the space-time outside of rotating objects which are not black hole. But as far as we know, only as an approximation. So until now, nobody has ever found a reasonable interior solution which can be matched to the Kerr solution. What does I mean? What do I mean by reasonable? Well, one can discuss what is reasonable and what is not. What I mean is, for instance, a ball, not a degenerate thing, really something which is three-dimensional in space. A ball with a surface and with a reasonable matter equation, say a perfect fluid. Yeah? Something like that does not exist. As far as I know, it has not been rigorously proven that it really doesn't exist mathematically. Until now, just nobody has found such an interior solution. There are a few no-go theorems, but I think it's not a general theorem of the kind, a thing which has a surface, so it is a three-dimensional area with a surface, and it has a positive matter model, say positive energy condition or something like that, that this cannot be matched to Kerr. As far as I know, such a theorem does not exist. But as I said, nobody has ever found this. So the kind of interior solutions, in quotation marks, which have been found for the Kerr metric are just disks. Yeah? You can match the Kerr metric to a disk, some kind of pathological disk, for instance, with a positive matter distribution on the upper side and a negative matter distribution on the lower side, which doesn't sound really convincing. Or two disks, one is rotating in this direction and the other one is rotating in this direction, but you consider the limits that they coincide. So this also works. These are the kinds of solutions, interior solutions, which have been found. All of them, look, highly pathological or, contrived. So nobody would think that something like that exists in nature. The only thing which can be approached by an interior solution, at least in the limiting sense, is the extreme Kerr solution. This can be reached by a family of reasonable disks, namely disks which are dust, so they have a positive matter density, positive energy density, and they are rigidly rotating. So you can construct a family, a one-parameter family of rigidly rotating dusts. These are called the Neugebauer-Meinl disks, after the gentleman who discovered this solution. And this can be, in the limit, that the parameter approaches a certain value. This approaches extremal Kerr metric. And it is believed that this only works for the extremal Kerr metric. There are general arguments that something like that probably does not work does not work for the non-extreme Kerr black hole with A strictly smaller than M. So why do I tell this at this point of the lectures? Because I want to discuss briefly the possibility of using this metric for objects which are not black hole, which are really stars or the Earth or something like that. And from what I have said right now, it's clear that this cannot be true in the strict sense. So we cannot use this really in the sense of an exact solution outside of the Earth or outside of the Sun or a star. Yeah? All celestial bodies rotate as far as we know. So the Schwarzschild solution is only an approximation in the sense that we neglect the rotation. If we take the rotation into account, the question is, can we use a Kerr metric for the exterior? And it can be used only as an approximation if we are sufficiently far away from the value m. So the r coordinate must be big in comparison to m. Then we can use it approximately. And then we can ask ourselves, can one observe effects of the geodesics, for instance, in the field of the Earth? And there's one famous effect which can be observed and has already been observed. That's the Lense-Thirring rotation of the orbital plane. So let me briefly explain what this is. So we consider now the geodesics in the Kerr metric far away from the center. And we use this as an approximation for the field, for instance, of the Earth. And then we look for qualitative effects which are new in comparison to what we know from Schwarzschild or even from Newton. And we ask ourselves, can we observe this? So what we can do is we use the Kerr metric as an approximation for the gravitational field of a non-collapsed, meaning not a black hole. Yeah, actually, well, from the general structure of the metric, it's clear that if you are far enough away from the center, then it must be a good approximation. If you look at the metric, you see it begins with a 1 over r term. This is the one we are used to from Schwarzschild. That's the so-called monopole term. Yeah, that's the first term which comes into play as a deviation from the flat metric. If you start at infinity and then move closer to the center. So the first thing is a gravitational monopole, the m term, m over r. And then the next term is a dipole term. That's the a term. A is the angular momentum, the specific angular momentum of the thing. So the next thing is a dipole term. And then come higher order terms. And they are for all rotating bodies which we know. They are different from the Kerr ones. So for the Kerr solution has a particular sequence of multiple moments. Here you can start with the 1 over r term, then comes the dipole term, and so on. You can do multiple terms of arbitrary order. And these will not be the multiple moments of any existing rotating body of the Earth or of stars or anything like that. But if I'm very far away, then the approximation where I have only the m and the a, this is a good approximation. And in this approximation, one could use the Kerr metric as an approximation for the gravitational field of a non-collapsed rotating body, as far as I'm far enough away from the thing. And then we could ask if we have observable effects which distinguishes the Kerr metric from the Schwarzschild metric. And what we see is the following. In the Schwarzschild metric, we have planar orbits. Every orbit is contained in a plane. And that's not the case in the Kerr metric. In the Kerr metric, what happens is, if we have such an orbit, which is a Kepler ellipse now slightly perturbed, well, the first thing which happens, if I consider a very big Kepler ellipse and now make it a little bit smaller, so that the Schwarzschild correction terms, correction to Newton, come into game, then I have the perihelion precession. Yeah? The Schwarzschild term, the 2m over r term, in the Schwarzschild metric, this causes perihelion precession. And now comes the a term. The question is, does the a term add a qualitatively new feature? And what it does is that the orbit is no longer in a plane. Yeah, not only the perihelion is precessing, the whole plane is precessing in addition. Yeah, the orbital plane is precessing. And that's what one calls the Lense-Thirring effect. And this is something which can actually be observed. So orbits are then no longer planar. The orbital plane precesses. And this is called Lense-Thirring effect, or Lense-Thirring precession. Named after the two gentlemen who found this. Actually, they found this long before the Kerr metric existed. They found this around 1917, I think, 17 or 18. And what they did is they used a certain approximation, a weak field approximation. They didn't work with an exact solution. They worked with a weak field approximation. And this is exactly the realm where the Kerr metric can be used as an approximation for the gravitational field of a non-collapsed body. So this is a range where this approximation is valid. By the way, this sometimes one hears funny pronunciation of these names. They were Austrian. Yeah? So it's not Lense-Thirring, so it's really Lense-Thirring. Hans Thirring was a famous theoretical physicist in Vienna, and then his son Walter Thirring carried along this tradition. Maybe some of you know these textbooks by Walter Thirring. That's the son on mathematical physics. So that was his father, Hans Thirring. And Lense was later a professor in Munich for many years. One of my teachers actually had heard lectures by Lense, who was, as he told me, was a very funny person, a very, very eccentric person. Okay, so they discovered this effect, and the question is, does this exist in nature? Can this be observed? And actually, it has been observed already in the field of the Earth. So, has been observed. This rotation of the plane has been observed by Lagios satellites. and by the so-called gravity probe B. Experiment. Actually, the name Lense-Thirring effect is sometimes used as a general word for all effects which are produced by the rotation of the central object. Yeah, so for instance, it drags the orbital plane. So that's the traditional Lense-Thirring effect, which was actually discussed in the work by Lense and Thirring. But there's also an effect on the spin. If you have a spinning particle, then also the spin is influenced by the central rotating body. This also goes under the name of Lense-Thirring effect. Although it was not discussed by Lense and Thirring, it was discussed much later by Schiff, I think around 1960. So it should be called the Schiff effect. This would be a better name. But sometimes Lense-Thirring effect goes as a general name for all this. So this is one of the relativistic effects which was observed comparatively recently. And this is an effect where it's really shown that the gravitational field of a rotating body is different from the gravitational field of the same body if it does not rotate. That's different from Newtonian theory, right? In Newtonian theory, it doesn't matter if a mass distribution rotates or not. Gravitational field is the same. Only the mass density matters. Yeah? But in gravity, in Einstein's gravitational theory, the fact that the source rotates brings another kind of energy into the game. And all sort of energy is a source for a gravitational field. Yeah? So it produces a new aspect for the gravitational field. And this manifests itself for instance, in the geodesic equation. And it can actually be observed. So this is this dragging which is produced by a rotating object. So the geodesics are dragged, and also the spin of particles are dragged. So all these names, all these things, they are associated with the fact that the source is rotating. And where there's a certain analogy between these effects and magnetic fields. So these effects, which are produced by the fact that the source rotates, they are related to ordinary gravitational effects in a similar way as magnetism is related to electric fields. Think of a charge distribution which is not rotating. It has an electric field. It has no magnetic field. If it rotates, it has also a magnetic field. Yeah? And in the same sense, a mass which is not rotating has a gravitational field which is qualitatively similar to what we know from Newtonian theory. But if it rotates, there are additional effects which are analogous to a magnetic field, and they are called gravitomagnetic effects. Just as an allusion to this analogy, effects produced by rotation of source are called gravitomagnetic. So the gravitomagnetic effects which are observed in the geodesics of the Kerr spacetime, they are the features which distinguish the Kerr metric from a non-rotating object. And actually, these gravitomagnetic effects, they are present not only in the Kerr metric, they are present in the field of any rotating object. The bad thing is that we know very little in terms of exact solutions for rotating objects. The Kerr solution is, according to everything we know, it's a field around a rotating black hole. As I said already, as far as we know, it's not the field of any other reasonable rotating object. And the field of a rotating star, not a collapsed object, really a star made out of a perfect fluid, for instance, with a certain pressure or so. Finding solutions for this is awfully complicated. Yeah, we know very little about really exact solutions which can be matched between an interior and exterior solution, and which are known everywhere in space and are regular everywhere. It's very, very difficult to find this. A lot of work on this subject is done in terms of numerical studies, but very little is known in terms of exact solutions. So the Kerr solution is really distinguished among all these rotating solutions, in a sense, by its simplicity. So the black hole is, in a sense, the simplest rotating object we can think of. It's really true. So for instance, if you look in the theory of neutron stars, yeah, it's much, much more complicated than the theory of black holes. Yeah? Black holes are comparatively simple objects. And you can more or less calculate everything analytically in the Kerr metric, which is a quite remarkable fact. So in particular, you can calculate the geodesic equation analytically, and what I've done, I'm already over time. What I've done in the last lecture and in this lecture was to give you a flavor of what the geodesics in the Kerr metric do. So if you want to study them in detail, you should plan with a couple of months, if not years, in order to go really into the matter more deeply. Okay, I'll stop with the geodesics and the lectures now. We will do another worksheet on this, about the time-lag geodesics. And on Friday, I will talk about this famous Penrose process, this process where you extract energy from a rotating black hole. And then I think next week, I only have time for doing the section on astrophysics of black holes. I will speak on the supermassive black holes and the stellar black holes, the observations. And then term is already over. In the last week, I will be away, so we have to stop at the end of next week with the course. So we have only 3 lectures. I try to fill them in a meaningful way. Okay, see you on Friday.